Now, we go to the concept of resistance that can be explained using Ohm's Law. The Ohm's Law for EMT is a little bit different compared to the Ohm's Law that you know in other courses because there is just a general form V equal to IR. But here, we define the resistance from the very fundamental using electric field, potential, and so on. Let's go. Let's say you have a conductor in the form of cylinder like this. Right. What happens if we apply the voltage source to the conductor? So the voltage source will supply the electric current through the conductor. And the voltage source also provide the impressed E field. So the potential between the both ends of the conductor, okay, let's say this point is A, this point is B, is equal to VAB. So this is our Y directions. The question is how to calculate the resistance for the conductor. Well, what we know, the resistance R is equal to VAV divided by I. Potential divided by current, and the unit is ohms. We know that the current I is equal to the integration of J dot ds. And we already derived that J is equal to sigma E dot ds. If our structures is symmetry, so we can simplify I into sigma EYS because here we have the same cross-section area. So that means the area is not changed throughout the structures. For potential, VAB is equal to negative integration of B to A E dot dl. Again, when we have the symmetrical structures where the cross-section area is not changed, the length also fixed like this. So we can simplify our VAB into EYL because our E in the direction of Y. Therefore, we can define our resistance R equal to L divided by sigma S. This is the resistance in conductor with uniform cross sections. So from this equation, we can see that the resistance is depend on the physical dimension and also the material properties of the conductor. When the conductor is longer, so the resistance will increase, and it is inversely proportional with the sigma and also the cross-section area. Alright, the general formula for resistance would be R equal to V divided by I is equal to negative E dot dl divided by J dot ds. So equal to negative integration of E dot dl divided by integration of sigma E dot ds. This is when we have, let's say we have a long wire that have a symmetrical shape. So we can simplify R into this form. But let's say we have a curved wire and so on. So we should use this equation. So as I mentioned earlier, resistance of the conductor depends on length, conductivity, and surface area of the conductor. For conductor with a non-uniform cross-section area, as shown in this figure, okay, we can see that the cross-section area varies from point A to point B. Therefore, we have to solve the integrations, okay, to find the resistance. The resistance is equal to the V divided by I, so the V is negative B to A E dot dl divided by J dot ds. So you have to solve the integrations. We cannot simply cancel out the E field and also to put just S, because for non-uniform cross-section area or non-uniform E and J, we have to solve the integration, because other than the surface itself varies, E and J can also varies, because E and J can vary in terms of variable. So it should be solved part by part. Let's see example 1. Find a resistance of a cylindrical metal having conductivity of 1 multiplied by 10 power of 7 Siemens per meter, with a radius of 1.5 centimeter and length of 3 cm. So for the solution, so we have symmetrical structures which is easy to be calculated. So L is equal to 3 cm, we have to convert to meter. Everything should be converted to meter. So L equal to 0.03 meter, and the cross-section area equal to S equal to pi r square equal to pi multiplied by 0.015 square. Because our radius is 1.5 cm, we have to convert to meter. And we have to insert into our formula. So R equal to L divided by sigma S, and our final answer will be 4.24 micro ohm.